All right, here we go for, and I almost promise this will be our last video for the day. Most of the work that we've been doing is to try and understand geometric picture-wise what it means for things to be linearly independent or coplanar or a spanning set. And really our homework is algebra like these questions. So if this is more comfortable and familiar, that's okay. I think the pictures though, the models will give you a deeper understanding, but certainly this is the sort of thing that you'll need to reproduce in your homework. Um, Show that W can be written as a linear combination of I, J, and K. I've got all this stuff written, so I'm going to go quickly as I can. Pause if you need to. This is the easy one, right? I, J, and K are spanning vectors for space, the easy ones, and I can write W as a linear combination of those vectors really easily because unit vector in the direction of x, unit vector in the direction of y, and in z, and bing, 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 there it is. But we've also seen that other vectors can be um, basis for space as well, spanning set for space. B, show that W can be written as a linear combination of U and V. So what that says is show that this can happen. So that means we must be able to find values of A and B, and so that this is true. And we'll see that we can. So algebraically, what do we got? We've got W equals AU plus BV, and then I end up actually with three equations. And it's almost like I got an extra one here, but I'll explain what's going on there. Um, the two of them from the x coordinate, right? A times 1 plus b times minus 1 equals the x coordinates. There's the y this is the x coordinate, y coordinate, and z coordinate of the vector, and then I get values of a and b that work. But the thing is what's going on with this one? I only used the first two and the two equations, two unknowns. I've got three equations and two unknowns. Well, I have to make sure. What I've found out is I found A and B values that work for the first two coordinates. I have to make sure it's going to work for the third as well. What's going on here? I have to make sure that this is going to work. I've got potential A and B values, but let's just see. The left side's minus 2, negative 3 times 2 minus 4 times minus 1, negative 6 plus 4. Yep, it works. Therefore, it works for x coordinates, y coordinates, and z coordinates. Therefore, W equals 2u minus v. There, I've written W as a linear combination of u and v. So what else does that mean? What else does that mean if it's a linear combination? Well, it means that they're coplanar, right? Picture the case where we had the piece of paper lying flat. What I've got is that W can be written as a linear combination, a combination of u and v. So they're on the same plane, which also means that the three vectors are linearly dependent. When they're on the same plane, it means they're linearly dependent, which also means they do not form a spanning set for space. Don't know what that was about. Let's just keep going. And that means they're not a basis. They're not a basis for space. The three of them define a plane, not space. Okay, because we found that they were linearly dependent, a linear combination of each other. And notice when I say one, I get all of them. Coplanar, linearly dependent, not a spanning set. All of them mean the same thing. Oh, look at that. The homework cloud's there. It's coming. But I still want to do part C here. Part C was to prove that Z cannot be written as a linear combination of U and V. And how am I going to do that? Well, I'm going to proceed in the same way. I'm going to try and do it, and hopefully something bad happens, and I say, therefore, I can't do it. And that's what I'm going to do. So I set up Z equals AU plus BV, and then I get three equations, three unknowns, and guess what's going to happen? From two of them, I get a value, potential values for A and B. So these are values that work for two coordinates. Does it matter which ones I use? No, I could use any one of them. I could try and solve some for by inspection, perhaps even sometimes I might be clever enough to find values that work for two coordinates by inspection. But in the third, what happens? I sub into the third, and those values that worked for the x and y coordinates, this was the x coordinate, this is the y coordinate, don't work for the z coordinate. So it was supposed to equal -2, but it works out to be something else. So this proves that z cannot be written as a linear combination of u and v. No values of a and b worked for all three coordinates. So what else does that mean? Well, this is what we showed. Z is not a linear combination of u and v. It means the three vectors, u, v, and w, are linearly independent. Remember in the last example, if they were a linear combination of each other, they were linearly dependent on each other. But if that's not the case, they're linearly independent, which means they're not on the same plane. And as soon as I have that they're not on the same plane, that means I've got my spanning set, and I can say that they're a basis of space. So if I wanted to prove that three vectors were a basis for space, or a spanning set for space, what I could show is that one of them is not a linear combination of the other two in the way that I've shown right here. Okay, good patience today, folks. Hopefully you got that nice dandy model there sitting on your desk and all is good. Good luck with the homework.